I've been at Rutgers for 10 years now. I had a great time. I apologize to some of you who have heard part of this before, but I'll try to get some new stuff in here. The subject of my talk is on this first slide, simulations of protein crystals. And the people on the top line are here in the audience, or Pavel is gone, but for people at Rutgers that did a lot with this. I spent my sabbatical last year in Princeton University in Nozomi Ando's lab working with postdoc Steve Meisberger as well. And you'll be seeing some results from that collaboration. And then toward the end, I'll talk about connections between molecular dynamics software that I work on, the AMBER programs and the Phoenix crystallographic refinement programs. And that's work with Nigel Moriarty and Paul Adams. So crystals are periodic systems. They're actually very attractive if you think about high quality or high precision biophysics measurements, because crystals are actually a very pure form often of biomolecules. I mean, you recrystallize things to purify them, and you have an array of protein molecules in a lattice, and they're all in the same environment. And so if you want to think about studying details of the properties of biomolecules, crystals are an excellent thing to do. From a computational perspective, and I guess I should say, for those of you that don't know, I'm a computational chemist. I work with computers and molecular dynamics simulations. And usually when you see molecular dynamics simulations, they're targeted at molecules in solution, biomolecules in solution, as in this kind of cartoon here. In the green in the center, you have a protein and a bunch of water molecules and ions and other things that are around it. But in practice, that simulation is not done just with a single protein molecule and a bunch of water molecules. It's actually itself a quasi-periodic system. Artificial periodicity is introduced such that there's a copy of the central thing tiled throughout space and in 3 dimensions as well as 2 that goes off to infinity. The reason for doing that in solution simulations is to avoid an air-water interface. Say here, if you didn't have the non-green things, then you'd have a vacuum outside here, and you'd have a large surface tension from water and a water vacuum interface. But since we're so used to doing this sort of simulation naturally anyway, it's quite obvious to think, well, we could do this for crystals as well. So in crystals, your periodicity now is not an artificial periodicity, it's a model of the actual periodicity that's in the physical system that you're trying to model. And so for the rest of the time, I guess the next thing is kind of, well, we can do it. I mean, here we have a hammer. We know how to do periodic simulations, and we do them all the time. But why would anyone want to do this sort of thing? And frankly, I'm coming at it from a computational perspective. For the green things at the top, I originally got interested in this as a way to test, compare, and improve force fields. So we know a lot about what the behavior of proteins in crystals is. We know their average structure to a high accuracy and precision. We know things about their motions and their fluctuations about this average structure, and a lot of other things that goes on. And so we can see how to do that. I'm not going to talk about any of that today, but that's actually a driving thing. A second kind of obvious thing to think about in molecular dynamics simulations is simulation of time-dependent events in crystals. And again, it's in green. I'm not going to talk about that, but nowadays, with Lowy spectroscopy and with the advent of X-ray free electron lasers, one can have very rapid experiments, time-resolved experiments in crystallography in crystals, such that time resolved down to femtosecond, picosecond, or nanosecond timescales that match kind of simulation timescales. And so it's actually not as straightforward as you might think to look at time-dependent events, but one can do that. The things I will talk about, though, are in red here. I'm going to talk some about diffuse scattering and crystalline disorder and the nature of because a crystal is not a perfect lattice that never has any imperfections or changes from one unit cell to the other, and we'll talk about that. And diffuse scattering essentially is analysis of where the X-ray photons, the scattered X-rays go when they don't go into Bragg peaks. So it's an analysis of all of the scattering of X-rays, except for the scattering of X-rays that traditionally is used to go into Bragg peaks. And then another reason for wanting to do crystal simulations is to help understand both what's going on in crystals in detail and crystallographic refinement methods. And I'll talk at the end about incorporation into Phoenix. I'm also interested in NMR can be done in the solid state, and there's and infrared or terahertz spectroscopy can also be done in crystals. And I'm interested in those things, and some of you might want to talk to me about that, but that's another subject that I'm not going to be presenting today. So a few years ago, about 5 or 6 years ago, we started with a very small, not even a peptide, not even a protein crystal, but a crystalline material of biomolecules that was originally synthesized in Isabel Carla's group and crystallized in the report a long time ago at the crystal structure, which is shown here. The unit cell of this small repeating peptide is just 2 peptide units and some water molecules shown right here. And so that would seem to be a test of, if we have a small, fairly simple, pretty rigid system, what can we learn and how well can we do? And so we started kind of at a small stage. This figure illustrates, however, that the actual simulation we do does not have a periodically, it uses a supercell. Shown here, there's a 3 by 3 copies or 9 copies of the unit cell here in a single plane, and then perpendicular to the slide, there's an additional level of periodicity. And the actual periodic repeating unit in the simulation is 36 of these unit cells. So it's 4 by 3 by 3 unit cells. Partially that's to get lots of copies of the peptide to work with, but remember that even though, think about crystallography, in crystallography, the average properties of every unit cell, which is right here, is the same as the average properties of every other unit cell. But instantaneously, in a dynamic simulation, the coordinates of the unit cells are not correlated with each other, or not in sync with each other. And so we're using a large number of unit cells in order to try to mimic what really is physically going on in crystals. So that on average, each unit cell has the same type of structure, but instantaneously they don't. And we're interested in correlated motions and what's going on that you can only describe by having a supercell that is actually several unit cells or a number of unit cells. And I'll have examples today of much bigger things. We've gone up to 343 unit cells as our periodically replicated system in the simulations. But this is just a start that we did a few years ago. And the simplest thing you can do is to say, when you do a simulation and you want to compare to experiment, how does the average structure in the simulation match the average structure in the experiment? And that's what's shown here on the left-hand slide of this figure ribbon diagram. So the orange is the crystallographically determined. This is almost a small molecule structure, so very high precision and accuracy in the coordinates. And the black is the black is the experiment, and the orange, which is almost indistinguishable, is the average structure in the simulation. And they're really, both the side chains and the backbone are kind of shown here, and they're really very close to each other, except we're at the very end of the second peptide. At valine 18, the side chain rotamer in the simulation on average is a little different than the one it is in the crystal. There's actually rotameric disorder at that position. And that change in the side chain, and there actually, you can't tell it from this picture, but we analyzed other things to show that that actually propagates to the little bit of difference here between black and gold in the C-terminal end of this. But this is really, in a sense, for a small, pretty rigid peptide simulation, we can do extraordinarily well, at least by the standards of computational chemistry. The backbone deviations between the crystallographic structure, which for the purposes of this is essentially arbitrarily accurate, and our simulation, the errors are all in the simulation, not in the residual uncertainties from the crystal structure. A typical snapshot, which you're not seeing here, you're seeing the average structure, but if you took a typical snapshot, the backbone atoms would be about half an angstrom away from their average position in the crystal. And that's expected. We have vibrational motion that's always going on. If you look at instantaneously at a protein or a peptide structure, it's never going to be exactly what its average structure is. But if you compare the average structures, then they're about 0.3 of an angstrom different. Now remember that a carbon-carbon bond is 1.5 angstroms average. So a 0.3 of an angstrom difference is 1/5 of the typical carbon-carbon bond length, or you can kind of see it here. There's really not much difference at all between the computed average structure and the experimental average structure. Really, of course, the crystallographic average structure came from an analysis of the electron density. X-rays don't scatter off atoms, they scatter off electrons. And so it's the average electron density in the crystal that is being modeled in the crystallographic structure. And so, in a sense, the better way to compare the calculation with the experiment is to calculate the average electron density in the simulation and then refine into that. Pretend that that was your experiment, do a refinement into that data to match your model. And when you do that, you come down some. This doesn't always happen, but you come down to about 0.2 of an angstrom. Now, in principle, this number could get as small as you like, but you're not going to see any numbers that are better than this. In fact, every number that you're going to see in a bigger system is considerably larger than this number because this is a small, nearly rigid system. But we can do a good job. Notice here, though, I'm not showing you any solvent. There's not a lot of solvent in these crystals. These are fairly dry, but there is water in these crystals. And what you're seeing here is just the peptide unit. If you take a little quick movie of what goes on, the black are the peptide units looking kind of down the helix, and the red molecules are the water. The black things just vibrate about their average structure, but the water molecules in these channels kind of diffuse out, and when they diffuse over here, of course, there's another copy of this set of the supercell over here. The water molecules don't just vibrate about their average structure. They diffuse in kind of the diffusional characteristic through these channels. We've analyzed that is diffusional motion, and you can kind of see that sort of thing, but it emphasizes the fact that solvent in protein crystals acts in a very different way than the protein themselves. The peptides actually just vibrate about an average structure, but the water molecules, in the individual water molecule, moves along. Yes, Hunter?
Is the crystal determined cryogenically, the structure?
No, this is. So everything I'm showing you today is room temperature crystallography and room temperature simulations. Part of the reason that we chose these samples is I can do a simulation at low temperature, but nothing happens, okay? I don't have enough thermal energy to move very far away from where I start, and so it's not very interesting to look at that. You know, there's a big arguments in crystallography about when you really need to do low temperature crystallography and when you can get away with room temperature structures. The principal reasons for doing low temperature crystallography in practice have to do with ease of sample handling and avoidance of radiation damage. Okay, the radiation damage from X-rays is much smaller at low temperatures than it is at high temperatures. But for a great many systems, you can actually do room temperature crystallography, and the crystals are just as good. The resolutions are just as high. If you can avoid radiation damage, and we'll talk a little bit about that later, then we can do experiments at room temperature. So I'm comparing room temperature simulations with room temperature spectroscopy today. So even though the water molecules are moving a lot, that doesn't mean they don't have preferred positions. They actually jump around from one preferred position to the next, and we can kind of see that on the next picture, which now here's the top of the peptide in the simulation and the top of the peptide or the bottom of the peptide in the crystal, and now you're seeing the contours of the electron density of the solvent channel in the simulation and in the crystal. And the red dots are where the crystallographers chose to put water molecules. So if you look at a PDB file of a protein, you'll see ordered water molecules, or something that says it's water. And it has a position that looks like just any other type of atom, has a B factor and so on. But that, as I emphasized, that doesn't mean it's just sitting there. In the bound state is usually jumping from one water position to the other. But actually the density, the simulated electron density for the water, as you can see, looks remarkably like the one in the crystal. There's a little dumbbell here and a dumbbell here, a sphere here and a sphere here, and so on. That the comparison of where the water likes to be in the simulation as with the peptide, actually is really quite remarkably good. So we concluded from this that one can, it's possible to get very good results. But if you go to bigger systems, which I'm doing next, you won't see quite as good a result. And the main reason is that the more ways you have to go wrong, the more likely is your simulation is going to find one of those ways to go wrong. And so bigger systems are almost never as close to experiment as the smaller systems are. But this gives us kind of a benchmark of what we'd like to be pushing toward. So lysozyme has been our workhorse test case for kind of real proteins. It says bigger, but of course the biologists among you will still say that lysozyme is really tiny, kind of a small protein, 129 residues in the thing. Here we have a P1, again a P1 symmetry. You're seeing just 6 copies of the protein here, but we in this and other simulations, this particular one we did 12 unit cells as our supercell. And we've gone up, you'll see later things up to, as I said, 343 unit cells are copies of the protein chain in our supercell unit cell. And here now, if you look at the comparison again of the average structure shown in the movie, and again, the black is the experimental average structure, and the orange is the average computed structure. It looks remarkably close. You'd say if you ever got a simulation that looked like this, you'd be hard pressed to say there was something wrong with it. It's a little bit cheating because here I'm only showing you the backbone, whereas in the small peptide, I was showing you the side chain atoms as well as the backbone atoms. And so the side chains don't fit as well as the backbone does for lysozyme. But still, the average structure here in the backbone, the atoms of the backbone is only 0.35 angstroms away from the average structure. And kind of, again, if you think about carbon-carbon bond lengths, or just look at this and say, we're probably not going to ever get any better than this sort of structure. And in fact, lysozyme still is our, for a real protein, is in our lab a benchmark to say, typically this kind of number, this difference between the average structure in the simulation and that in the crystallography is like twice this big, even for well-folded proteins, and it can get worse than that for floppier proteins and so on. So this is kind of still a good case. The other kind of simple thing to do to compare simulation and experiment, just to see how well are we doing, is to look at fluctuations about the average structure. So we have an average structure that you saw in that previous movie. If one considers fluctuations about it for the protein atoms, then that's reflected in the B factors or the atomic displacement parameters that you see in PDB files. So what's shown here is a function of amino acids from 1 to 129 amino acids is the isotropic B factor for the C alpha atoms of every residue in this protein. And the black numbers, the black is the experimental, again from a room temperature crystallography, actually sub 1 angstrom resolution. So this is extremely highly refined and accurate data. And the colored numbers are from the calculations. And the first thing you can see is that for the most part, there's actually pretty good agreement, quantitative agreement between the simulation and the experiment. And the most part excludes the N-terminal region, which I'll talk about in just a minute. But if you look at the other places, the red, purple, and black curves are almost all the same. There's a couple of places here where the purple curve gets to be a lot bigger than the black curve. But overall, again, this is better than you will do for most of the other protein in terms of agreement. There's no fudge factor here. There's no up and down swap of the fitting the experimental data to the calculated data. These are absolute B factors calculated from the simulation compared with the actual B factors that are refined in the simulation. The two different colored curves are interesting to think about. The purple curve is just saying what I said before, which is not quite right, that the B factors represent fluctuations of the atoms about their average position. And that's close to being correct, but I'll explain why it's not quite correct in a minute. But the red curve, the purple curve says that I'm just going to calculate the fluctuations. I'm going to actually calculate the root mean square fluctuation of every C alpha atom about its average position in the simulation and plot that as a B factor. And that again, and basically I'm not going to say, we know actually, I should say, we kind of understand structurally what went wrong here. There's a loop at around residues 9 to 12 that moved into a different configuration in the calculation than it is in the experiment. And that led to larger B factors in this region. And the other place, though, the purple curve, you have very large fluctuations in some of these. These are other loops. These are positions. The low, as you may, those of you that have studied proteins a lot, low B factors tend to be in regions of secondary structure. There's not as much fluctuation in relatively rigid secondary structures. And in the loops in between secondary structure regions, you have larger fluctuations. So the peaks in this kind of curve correspond to loops in the secondary structure. And there's places around residue 100 and around residue 40 and so on where there are large fluctuations. But B factors, in a better sense, are actually a refinement parameter. They're not just fluctuations. They represent fluctuations, but you are fitting B factors and atomic coordinates to experimental data in the black curve. And B factors tend to take up some of the experimental slop for other things that your model doesn't really represent very well. And so if there's a deficiency in your model, not to mention deficiency in the experimental data, then the B factor might not represent the fluctuations. And that's shown here in these loop positions where you have very large fluctuations. These actually do have large fluctuations, but if the red curve is what I said before. I took the average electron density from the simulation, pretended that was my experiment, and refined my model into it. And so the refined B factors are the red curves here, which are actually much closer to the black curve, indicating that in these positions, probably the reason that the black curve and the red curve are lower than the true fluctuation in the simulation, is because the refinement is using B factors to take up slop and other sorts of errors. And so it's a limitation of the model. This is not a new idea. People have known for quite some time that when you have large fluctuations and floppy regions in a protein, the B factors that you get from fitting data will likely underestimate the true fluctuations of those things. So I'm not going to go on any more about this, but we're thinking about problems like this quite a bit. This is another one that kind of is a segue into my next section. We had in this simulation, we had 12 different individual unit cells. And when you looked at the positions, just the center of mass position of each of the unit cells as a function of time, the lattice wasn't quite correct. The lattice, the arrangement, and I'm just thinking now about the center of mass of each protein chain. So I'm not talking about any changes in loops or other things like that. Just where is the protein sitting in the lattice? And if a perfect lattice, all the proteins would be sitting exactly at 0, 0, 0. I'm projecting this onto the B axis and the C axis of the crystal, so you're not seeing the A axis. But the center of mass in a perfectly crystal, with no motion at all, the ideal crystal would just have everything right at the center. That's the structure I actually started from. I started from a perfect crystal structure and then allowed molecular dynamics to take place. Each of the different colors here represents one of the 12 unit cells in my simulation, and they all do different things. And there's really two types of lattice distortion that are taking place here. And it's worth thinking about that just in terms of what biomolecules really do. There's kind of a static disorder. The yellow curve here and the red curve and the cloud of, so for each color, then there's 100 snapshots of 100 randomly selected snapshots of where the protein was at that point. And the average of the yellow is out here, and the average of the blue is over here, and the average of the red is over here. And those don't really change very much as the simulation goes along. That's kind of like a static disorder. The lattice has become a little bit modified from an ideal lattice, and different unit cells are actually sitting, even on average, at different spots around that lattice. Now, the error is not very great. This is again, maybe 0.3 of an angstrom error in the center of mass of the entire protein. Okay, so that's, you looked at a video of this, you couldn't even see it. Okay, that's, again, a small fraction of a carbon-carbon bond length, but it will turn out to be important later on. And so, the static disorder kind of is that static for the time period of the 2 microseconds that we did this particular simulation for. It wouldn't be potentially static if I ran simulations for much longer time periods. But for the time of the simulation, the yellow curve is always different than the blue curve and the red curve and so on. And that's kind of just an indication that the lattice is after it's equilibrated, is not quite perfect because my force field is not quite perfect. But even within a given color, there, you still vibrate, the center of mass of the protein is still vibrating around an average position, it's still fluctuating about an average position, and that's thermal motion. You're never going to get rid of the spread. You might have a perfect simulation in which all of the different colors were really on top of each other and they were all centered right at 0, 0, 0. That would be kind of your ideal perfect simulation. But even in a perfect simulation, you would still have thermal motion, that the center of mass of any individual chain would be moving as a function of time. And that's the spread of the yellow numbers about their average position. And in this simulation, those two things are about equal in magnitude. The difference of the centers of mass of different colors is a quarter of an angstroms or so, and the spread of any individual color about its average is about a quarter of an angstrom. Now, I don't know if that's going to be true for other types of simulations or not, but we have thermal motion, which doesn't imply any disorder or imperfection in the crystal. Even a perfect crystal and a perfect simulation would still have thermal motion. A better simulation presumably would have less spread of the different colors. So why is anybody interested in tiny quarter of an angstrom changes in the center of mass of a lysozyme molecule in the middle of a crystal? And I wouldn't have been interested in that until a few years ago. But it turns out that imperfections, deviations from an ideal behavior actually is the cause of scattering of X-ray photons in places other than the Bragg peaks. So let's talk a little bit about scattering of X-rays. And as I said before, X-rays scatter off electrons. And if you had kind of a well-ordered, kind of perfect crystal, and not only just well-ordered, but kind of ideal crystal, then as you look at your thing, you would see only Bragg peaks. And in fact, you can show that you get delta functions and so on. And essentially, the Bragg peaks in a completely ideal lattice where every unit cell is exactly the same as every other unit cell, then all of your scattering just goes into the Bragg peaks. But if you have any kind of disorder, and the disorder can be thermal motion disorder about an ideal lattice or imperfections as kind of shown in this cartoon, the two types of disorder that I was talking about in the previous slide, then that we still have Bragg peaks for a lot of the things, but then there'll be so-called diffuse scattering between the things. And essentially the diffuse scattering is saying how different at any point in time or any point in space is the scattering factor from the crystal compared to its average. What's the standard deviation or the variance of the structure factors about their average position? Okay, and of course, in an ideal crystal, there's no variance, and so there's no diffuse scattering. But in real crystals and in real simulations, there certainly is deviations from ideality, and that leads to scattering in between the Bragg peaks. People don't actually know very much about this. One of the reasons it's interesting to me as a theoretical person is that I don't know how important this is going to be or how much biological insight we're going to be able to get out of this thing. And to a good extent, that's because no one has ever been able to really measure diffuse scattering in macromolecules very well until very recently. And that's primarily related to detectors. So back in the old days, one used film or image plates. And 20 years ago or so, you had charge coupled detectors. And only relatively recently, from maybe 2012 or so on, do we have what are called pixel array detectors, where you have individual pixels that can count photons. They have very small point spreads, so they're very narrow and accurate and precise in exactly what angle is the X-ray scattering going into. And they also have an extremely wide dynamic range. So the pixel array detector doesn't overload if you put too many photons in it, and it can go down to measuring something like 1 photon per second being scattered into it with very high accuracy and very low noise. So for the first time, within the last 3 or 4 years, these have come online in almost every synchrotron and free electron laser facility, and we have the ability to actually accurately measure not only what goes into the intense Bragg peaks, but where all the other photons going. And that's just kind of an interesting thing, just from a point of view of, I'll come to why I think this might be actually really useful information. But we measured, I should say, Steve Meisberger and Nozomi Ando, my sabbatical partners, actually did the measurements, and I did the simulations on a bunch of small kind of single domain proteins to kind of just get a survey for the first time with modern detectors of what's going into diffuse scattering. And I'm going to concentrate on lysozyme, the test case that I've chosen to talk about today. So here are some examples. The lysozyme can be crystallized in a variety of crystal forms. Doesn't make much difference for today's talk because all three of the crystal forms are kind of the same. What's plotted here as a function of scattering angle or resolution. So low resolution peaks are on the left, high resolution, about 1 angstrom resolution peaks are on the right. So I'm just giving you the scattering angle or the momentum transfer. And shown in kind of the brown is the Bragg scattering averaged over a bunch of peaks. And you can see that at low resolution, you can put a bit of Bragg peaks kind of in the median. And then at high resolution, the Bragg peaks drop off. That's the resolution limit that you see when you look at a PDB file that says what resolution was I used. And it's the Bragg peaks that were used to determine everything in the PDB file, the B factors and the crystal structure and all the other properties of the crystal came from an analysis of what would the scattering have been in an ideal lattice. And then on top of this, the blue peaks are the diffuse scattering. And it's actually non-negligible over the entire range and gets quite a bit larger as you get out to 1 angstrom even for lysozyme crystals. Gets quite a bit larger than the Bragg peak. So the diffuse scattering keeps going out to higher angles. And in fact, in these experiments, we made the mistake of cutting off the detector too far. The Bragg scattering goes way past where the detector went, but we know that. And it's actually, there's a little table here at the bottom right that kind of tells you where things are. If you're at 3 angstroms resolution, so you're cutting it off right about in here or so, then a third of the scattered photons go into Bragg peaks and 2/3 go into diffuse peaks. There's also an incoherent or inelastic scattering of some photons, which we're not going to analyze or talk about any further. As you go down to 1.2 angstrom resolution, only 10% of the scattered photons are going into the Bragg peaks that you're measuring. And again, about 2/3 of them are diffuse. And at higher resolution, you get more not inelastically scattered photons as well. So that there's potentially a lot of information in the diffuse scattering because most of the photons are not going into Bragg peaks. They're going into diffuse scattering. Now, there's a lot of places in between Bragg peaks. So in the individual pixel or spot in angle space is not going to get a lot of diffuse scattering. That's why we need good detectors that can measure very small photon fluxes. And the Bragg peaks are intense because even if they're only getting 10% of the photons, they're taking up much less than 10% of the scattering position. And so there's only a few places where you have Bragg peaks, a few thousand places or tens of thousands of places, but that's a small fraction of the total possible places that a scattered X-ray photon could go. So here's a picture of triclinic lysozyme in reciprocal space. So I'm showing you essentially analyzing in cutting through HKL space. L is equal to 0 and H is plotted here in this side, and L is, or K is plotted on the horizontal axis. So you're seeing a heat map of where all the photons go. And I'm just going to blow up on the next slide so we can talk about it more, the red rectangle in that sense. And so here we are in a piece of the thing. Now, all the little white spots here are potential Bragg spots in the diffusion, and they've been masked out. They're white, but that doesn't mean that they're any particular color. We subtracted out all the Bragg peaks to make this picture. Okay, they would, in many cases, they would be very intense relative to this. And then there's a heat map where yellow is intense and blue is the least intense. And you can kind of see that if you then forget about the white spots, which were already been analyzed and deposited crystal structures, and just think about where is the diffuse scattering going. There is kind of a, quote, diffuse character to this. Diffuse is a funny word because technically it just means anything that's not a Bragg peak is a diffuse peak in crystallography. But diffuse also in the English language means kind of slowly varying or dull or broad or something. And there is a slowly varying component. If you kind of go out in this direction from low resolution at the center of the thing to a high resolution at the corners, it kind of goes from blue to green and then back to blue again. And so there is a slowly varying, and that's kind of uniform. If you go and you look at the green stuff here, it doesn't change very quickly. So there's kind of a, not completely uniform, but a slowly varying component to diffuse scattering. And then there are these sharp yellow things by the particular color that's used on, the false color that's used here, is that there are sharply moving, there are quickly changing aspects of diffuse scattering, and they tend to be centered around Bragg peaks. So we call them halos. So around here, you're not seeing the Bragg peak, but there's an intense yellow thing. There's not yellow everywhere. It's just yellow around the Bragg peak. There's occasionally a few things in between Bragg peaks, like streaks and so on. But most of the sharply, quickly varying aspect of diffuse scattering comes in the halos. Okay, so that we kind of, as a simple idea, think that there is, in fact, a slowly varying component of diffuse scattering and a quickly varying component of diffuse scattering. And the quickly varying component is very tightly connected to the Bragg peaks. It's at the position of the Bragg peaks, and as I'll show you in a second, is correlated with the intensity of the Bragg peaks. So here is just, just to prove I can do it, we did calculations with various numbers of unit cells in the supercell. Okay, and the more unit cells you have in your supercell, the more finely you can look at the interior of the thing to see what's happening. And so by the time you get out to 7 by 7 by 7, which is 343 supercells, you're starting, and you won't see this in detail, but we've looked at it, you're starting to see things that look like experiment. I'm going to actually skip the bottom two things here and just go to the next slide. Whoops, no, I'm not, okay. So that we have that. And if you look at the slowly varying part is kind of what's shown in the bottom thing, again, as a function of the scattering angle from 0 scattering angle with the beam stop here at the left out to about 1 angstrom scattering angle on the right. And what the experiment is in black. And so the average is kind of this, and the calculation is there, and we're actually pretty happy with this. And I guess I should say, one thing that I didn't say here again, there's no fudge factor here. We were able with the new detectors to actually calibrate both Bragg peaks and diffuse peaks on an absolute scale. So there's no scale, there's no arbitrary scaling factor in the intensity. We know how many squared electrons per unit cell are effectively scattering our electrons out there, and that's an absolute number. Now they're shifted, the plot has shifted the blue curve relative to the black curve just so you can see it, but if you put the two on top of each other, it would be really on top of each other. So we know that not only is the shape of the blue curve, which is the calculated value, the same as the shape of the black curve, but the absolute intensities are correct as well, which is a thing that you don't always get. In the calculation, we can just remove the water molecules. So water, if you think about what kind of thing is causing disorder amongst different unit cells and crystals, well, you wouldn't even expect the solvent to be in the same place in one unit cell as the next unit cell. You might think that protein is supposed to be very close to itself, but the solvent molecules are mobile and moving around, and they're liquid-like, and they have some sizable channels. And so you wouldn't expect a perfect lattice, even kind of in your mind's eye of what do you think a perfect lattice would be. You wouldn't expect that the solvent would be the same in every unit cell. And so and that's kind of shown here. If I take out the solvent and just do a protein-only calculation, that's red here compared to actually the black here is the same as the blue here. The full calculation there. So I of course, can't take the solvent out of the actual experiment, but in my simulation, I can just strip all the waters out and recalculate the scattering. And it shows you that most of the slowly varying diffuse component, which is the blue, green, blue level, so low, high, low is blue, green, blue, in the upper figure, is really coming from the water. Okay, now there's a non-negligible, it's not a completely negligible protein contribution because proteins are moving and they're floppy and they're not exactly ideally ordered, but most of the slowly varying diffuse things are coming from solvent. Yeah.
Does the protein move more by moving the water?
No. So I didn't do that. We can't do a simulation just like you can't do an experiment without the water. You can't do a reasonable simulation without the water. What I did was take the simulation with water and just strip all the protein out, strip all the water molecules out, and then I had just a series of snapshots. I just threw away the waters in those snapshots. So I didn't rerun the simulation without solvent. I just reanalyzed the same simulation by removing their contribution to the scattering. Okay. So is this actually going to be interesting to know what happens? And I think the answer is yes, but you're going to have to come back next year or some other time to find out the answer. The key intriguing observation is the following that I didn't show you. I don't have a slide to show you this, but the intensity of the halos, remember, whoops, oh shoot. The intensity of these little yellow peaks around here is actually very strongly correlated with the intensity of the Bragg peak that you're not seeing in this picture. So we have, in a way, we have two different ways to measure Bragg intensities. One is to really measure Bragg intensities, and the other is to measure halo intensities, which are not at the Bragg peaks, but they're close to the Bragg peaks, and then correcting those. There's a scaling factor, multiplicative constant that connects one to the other, and it's a resolution dependent thing. But we think we understand what's going on there. And so that would give you extra information that would be kind of qualitatively or information content similar to Bragg intensities, a pseudo Bragg intensity. And then the real exciting thing, which has been done a little bit, but not very much, is I mentioned that the diffuse intensities go out to higher angles. So potentially you could be measuring pseudo Bragg peaks. You could be measuring halos out at high resolution angles where you could no longer measure Bragg peaks. So in principle, you have the ability to extend resolution. Now, I don't have a result to show you that that's really going to work yet. The key question is how accurate does the relationship between the halo intensity and the Bragg intensity have to be for that to be a useful number? Because it's not going to be a perfect relationship, and there's going to be some noise in that. And the unfortunate thing is we just don't know the answer to that yet. So a couple questions, I guess, yeah.
So in this image,
yeah.
Are the diffuse being intense because the reflections are also very intense that are hidden from us?
Can you say that again?
In the diffuse scattering, very intense.
Yeah.
Because the Bragg peaks are also intense, but they're not seen in this image.
That's right, essentially. And we think, of course, that why would the diffuse intensity of the yellow peak, why should you expect that to be related to the intensity of the Bragg peak? And that's a whole another talk that I don't have time to talk about that. But there are reasons, or there are models of what's going on in crystals that would predict that sort of behavior. So I want to move away from diffuse scattering. Yeah, but go ahead.
Technical question.
Yeah.
Simulation.
Yeah.
So do you take the number of water solvent molecules from the Bragg peaks and then, or do you allow, because you can imagine that just by changing the number you get this.
Right. So there's two things we can do. What we actually do in these simulations is adjust the number of water molecules so that the size of the unit cell in the simulation comes out to be the size of the unit cell in the experiment. Okay, if you put too many waters in, the unit cell will expand. If you put too few waters in, the unit cell will contract. And so it's kind of an arbitrary thing. Oops, sorry. Kind of a fudge factor that we say, okay, we're going to decide, because we don't know exactly how many waters are in. There's roughly pretty close to 290 water molecules for every protein chain in this lysozyme crystal, but we don't know. And we think we know that to plus or minus 1 or 2 waters per chain, but that's making that thing go back. If you have absolute intensities, you can actually calculate the total number of electrons in the unit cell. You know how many electrons are in the lysozyme chain because you know its chemical composition, and by subtraction you can figure out, assuming it's all water, you can figure out how many water molecules there are. That's so far less precise way of getting the number of water molecules, but they both really pretty much agree with each other. Okay, but these particular simulations were done with the first method. So I want to go back to Bragg intensities and conventional crystallography now, because I kind of apologize. The diffuse thing left you hanging. But it's interesting, I think. I mean, I look at it as interesting because it's just something no one knows very much about. 2/3 of the photons go to diffuse peaks, but nobody knows, either experimentally or computationally, how much information content is in there. And that's what we're pushing to figure out. You go back to think about what happens in crystallography. Really, it's a probabilistic. You can think of crystallographic refinement. So this is not solving the phase problem or solving the structure, but this is refining the structure. Once you kind of know how the molecules fit into the lattice and you have a rough structure, then the final aspect of getting a refined structure is to adjust by small amounts the coordinates and the B factors and other estimates of your model to get the best fit to the experimental data. And you can think that you'd like to know what's the probability, or like to maximize the probability that given the data, given the X-ray experimental Bragg intensities that you have, what's the probability that a particular model would have given that data? You have that model given that data, okay? And that's the thing you're trying to maximize. This is a maximum likelihood thing. And by Bayes' law, that's the probability that a particular model would have given that data, which we can calculate. We know how X-rays scatter off electrons. So actually this number, a maximum likelihood estimate, or a likelihood estimate of that number, the probability of that number, is something you can calculate. One of the nice things about crystallography and X-ray scattering compared to, say, NMR is that we understand to a very high degree of accuracy how X-rays get scattered. X-rays scatter off electrons, and it just matters where the electrons are. It doesn't matter even what atom the electron is in. It doesn't matter whether it's a hydrogen bond or a carbon or an oxygen or so on. It's just where the electrons are. Because an X-ray, at these energies, X-rays more or less scatter off electrons independently of where any other electron is. So if you know a model, you can calculate what data you should get from that model. Now there's experimental errors, there's uncertainty in the exact place where the beam is, there's jitter, there's fluctuations even in the frequency of the photons. There's all kinds of things that make it a little more complicated than I said. But one can have a model, a probability function that says, if this was the model, how likely is it that I would have gotten the data that I saw? And then by Bayes' rule, I have to multiply that by the probability of finding that model in the first place, okay? And divide by the probability that I would have gotten that data in the first place. Well, for a given experiment, the data is fixed, so I can ignore that with logs. I mean, that's just a constant in the denominator. And so, as I said, the probability of the data given the model is the maximum likelihood target that's encoded into crystallographic refinement models. And yeah.
I want to ask a question
Yeah.
about the probability of data.
Yeah.
You mentioned that is fixed given a experiment. Because mathematically it's equal to the integration of numerator over all models, right?
Yeah, but
so is this two always the same, or?
No, I'm just saying that for a given data set, we don't have to, we've taken the data and we found the data, we measured the data. So we don't have to, this is just a constant. And we don't really have to know what that constant is. If we're going to maximize, if we want to maximize the left-hand side, it doesn't matter what that constant is. Now, for other types of experiments, people are actually very interested in what's the probability of the data. But for the final refinement step of crystallography, you can think, well, I have the data. You know, you can say, well, if I go back and remeasure the data a year later, do I get the same answer? And that's another interesting question, but kind of aside from what I'm doing here. And the probability of the model, well, that's kind of a hard thing, but roughly speaking, the Boltzmann distribution tells you the probability of having a particular configuration of a protein. If you know the molecular mechanics energy of the protein. I can calculate that from the model and divide by some KT. Then by Boltzmann's law, that's the thermal equilibrium is the likelihood that I'll get that model. So I could actually do this, and taking logs means essentially that I add together the maximum likelihood. That's the likelihood that from the experiment, that's like a pseudo energy related to the experiment, and this is like an actual molecular mechanics energy. Conventionally, people don't do this. For this term, the likelihood of the model, they just have crystallographers use geometric restraints. I mean, bond length and bond angle restraints, and something that says two atoms can't be on top of each other. And they derive that from small molecule crystals, and that kind of stands in as the likelihood of the model. So what we've been exploring, and I only have a few minutes left, is suppose instead of using conventional Engen-Huber is the name of the geometric restraints that are typically used, suppose I used a force field instead and did exactly this calculation. Why would I want to do this? Well, it tells you how important are bond length constraints relative to angle bending constraints. Well, a force field tells you how much energy it takes to stretch a bond and how much energy it takes to move an angle and what the relative energies of those two are. You might not have small molecules to work for. If you like, and you think about this as a prior, this is the prior and this is the posterior in a base language, a force field energy, and eventually maybe we have to have better force fields for this to really be true, but somehow a force field energy is really encoding what we know about protein structure. It's telling you, the force field should be able to distinguish good protein conformations from bad protein conformations, and it's a way of encoding the prior information. So we did that, and I mean, this essentially has it has a long history. Most of what I did and the Phoenix people did is automate this procedure so that if you know how to run Phoenix, you don't have to learn Amber as well. You just say use Amber equals true and put some commands in and do everything else that you would ordinarily do in Phoenix. And so you can run paired refinements. You can try it the regular way, and you can try it with using Amber instead of the regular restraints and just see what the differences are. And we did that. It's automated enough that we could do 13,000 different paired protein refinements this way. And looking at the geometry. So the overall mole probity is a suite of things that says how good from empirical evidence and from high resolution protein crystals and so on, what is the overall geometric quality score for various conformations. And it's roughly speaking that the mole probity score gives you a very rough idea of what you would expect at a given resolution to get that kind of structure. And so CDL is the name for the conventional restraints that are used. And so we did these 13,000 as a function. Some of them went from 3.5 or 3 angstrom resolution down to sub 1 angstrom resolution, these paired refinements. And lower scores are better because higher resolution means a lower number. And so the conventional restraints on average in each bin look like this. And the Amber restraints typically are considerably lower. Okay, so that systematically, if you do this Amber refinement, you get a structure that mole probity and other measures of structural quality would say is a better number. A particularly interesting one of those, again, it's the same type of plot, is the number of H bonds per 100 residues. Okay, and you see here that the conventional numbers and the red are the Amber refinement. So at high resolution, it doesn't make much difference. At high resolution, nothing makes any difference. At high resolution, you can see every atom just in the density, electron density map, and you don't have to do anything. The refinement doesn't have much effect, and so these numbers are the same. But as you go to low resolution, kind of the red number stays about the same. On average, the number of hydrogen bonds per 100 residues doesn't depend upon the size of the protein or the resolution of the crystal structure. It's just a factor of crystallography, and so we kind of see that. But you lose, if you don't know anything about hydrogen bonds, and these conventional geometric restraints don't know anything about hydrogen bonds, then you lose a lot at low resolution. So as you go to low resolution and you do conventional refinements, you're not finding hydrogen bonds, and most of these hydrogen bonds that you're missing are secondary structure hydrogen bonds. You actually get better secondary structures when you refine with a force field that knows about secondary structures. Now you got to be careful because these force fields are obviously not perfect. I mean, I showed you some great examples for lysozyme at the beginning, but over the whole range of top possible proteins, you can't expect the amber force field or anybody else's force field to always be accurate. Are you paying any penalty if you get better geometries and we think you get better secondary structures, and you're really not paying much penalty in the agreement with experimental data? So there's lots of ways that you can compare how well does your structure predict the experimental data, but our free and our work are kind of statistics that the higher they are, the worse agreement you have with experiment. And again, red and blue for our free and blue and green for our work are nearly the same in both cases. So we've been systematically able to get higher quality structures as measured by things like malprobity without paying much penalty for agreement with experiment. Out of the many structures, especially at low resolution, there's lots of structures that more or less match the experimental X-ray data equally well. And the hope is that either now or in the future, force fields will get good enough that you can reliably say, amongst the structures that kind of fit the experimental data equally well, I should prefer to look at structures that have good force field energies, because my force field is at least accurate enough to tell good things from bad things. And we're on our way there. What I'm hoping, of course, is that people will try this on their own structures and see what happens and tell me what doesn't happen. I'm going to skip that a little bit. Let's see. Let me just say what we're working on. And some of the things that are kind of wrong with this and issues that my group is spending a lot of time trying to figure out right now. We don't know where all the waters are. In fact, a model in the PDB, as I said, in lysozyme there are 290, we think, roughly 290 water molecules for every protein chain. But there's only a few dozen water molecules that are found in the PDB file for lysozyme, because most of them are disordered and you can't locate them by any reasonable thing. So if you just have a few waters, they're not going to be happy in a force field, because the waters are only happy if they can make roughly 4 hydrogen bonds with neighboring waters. And if you don't have all the neighboring waters, then the waters that are there are not going to be happy in your force field. And so that's something that we have some ideas about how to go about that, but we haven't figured that out. Electrostatics may be overestimated again because the dielectric screening of these missing waters is missing from your force field. And so you may be overestimating electric things. The criteria for choosing the optimal weights. So weight, in spite of the fact that I said, if you like this effective temperature in the Boltzmann thing or something, how much should I give emphasis to having a good force field energy, and how much should I give emphasis to having a good R and R free or X-ray energy? And that comes up in NMR refinement, it comes up in crystallographic refinement. It's a real problem. You can say the answer is all tied up into how bad is your force field, how bad is your experimental measurements, and then what do you think you want? How are you trying to? How much do you believe computational chemistry? More or less, it comes down to a sociological problem. Are you willing to say, I'll give up a little bit of agreement with experiment in order to get what looks like a much better structure by other measures? And different people will have different answers to that question. We're really actually working now. I showed you high resolution data today, and lysozyme and the small peptide were both 1 angstrom like structures. But as you saw from some of the slides, some of the real prospect here is for low resolution refinement. And so we're working hard to incorporate this into both real space refinement at low resolutions, and to real space refinement. That kind of means you can work on cryo-EM model refinement as well as low resolution crystallographic refinement. Those are two areas that kind of have a lot of overlap and a lot of potential for improvement by paying more attention to what kind of models that you're actually building. And then, if any of you actually are brave enough to actually try this, and it's in the released versions of Phoenix, you actually literally do just say use amber equals true and a couple other things, and you can do it. And unfortunately, things won't always work right. Okay, and you got to be prepared for the fact that we're actually saying I'm going to make a force field description of more or less anything that's in the protein data bank. And if you thought about that, you realize that we can't really do that. We don't know how to handle metals. We don't know how to handle carbohydrates very well. There's funny things in the PDB. There's missing gaps and atoms. There's things you don't even really know what it is. We can't possibly have this completely automated. And so one of the things, but you know, user feedback is really helpful because we know we have to both make the program work in a better sense, but also document why it went wrong and make sure that you understand that it went wrong when it does go wrong. But aside from that, I think there's a lot of fun in doing these things that I've done, and I'll be happy to take some questions. Start here. Yeah.
Can you say a little more about what goes into the mole probity score?
Sure. So this comes out of the Richardson lab at Duke. The mole probity score is an overall score. There's clashes. So a large part of that is how many bad clashes, how many Ramachandran phi-psi angles are in approved regions. There's side chain rotamers that are in unusual positions, and they have an idea of what's a wrong rotamer position and a right rotamer position. So it's primarily local geometry. So the mole probity doesn't know if the overall fold of your beta sheets are in registration correctly, or all kinds of other things, or even if you have or don't have secondary hydrogen bonds, because you can either have one or not. So they don't know that. So mole probity is a measure of how good the local geometry is. But there are other things, we think for other reasons, not just local geometry, that we're getting better structures as well. So there's other quality measurements that we're trying to look at. You know, in a very simple sense, you'll say, if you look at a PDB file, there's these quality sliders that go from blue to red at the very beginning. You're going to get almost always better sliders if you do it with amber force field, just because we're putting more emphasis on getting that sort of thing right. The penalty for having a bad atom-atom clash is much bigger in a force field than it is in conventional restraints. And that's partially, again, sociological. People didn't think they had to put such big restraints on clashes. And so, and maybe they're right. But that's kind of what mole probity is doing. Eddie, and then I'll get some other, oh, sorry.
Well, I'll just shout out.
Stream.
Okay.
Dave, thank you for this fascinating and excellent seminar. Yeah, a lot of interesting insights, including the sort of deviation about lattice positions that's different for the different, you know, unit cells in your simulation. So of course, when you get very high resolution, you can also do anisotropic refinement. And perhaps in that peptide example from Isabella Carl, you had anisotropic thermal factors to work with. How does that help? This is where you have thermal motion rather than isotropic. You actually have these little thermal ellipsoids for each atom. Presumably you looked a bit at that. Did that improve the fit with the simulation?
Yes, it does. So more or less going from isotropic atomic displacement parameters, or B factors, to anisotropic looks pretty much the same whether you're using an amber force field or the conventional force field. You get about the same lowering of the R and R free factors and so on. We certainly did all of these high resolution simulations as that. I guess one thing that you could say is, if you refine into, I didn't say this, but maybe it'll be helpful to the crystallographers. If I refine into the experimental electron density, then with anisotropic B factors for a lysozyme-like protein, I get our work values around 15%. Whereas if I did the same protein but against the experimental density, I would get R free of around 11%. So a single model with anisotropic B factors matches the experiment better than it does the calculated density. And that's because there's these lattice imperfections. The density in the simulation doesn't look as much like a single model can't explain as much of it as you might. But the difference is not enormous. I mean, that's a few percent in our work or our free. It's not a, not going from uninterpretable to interpretable or something. So we still have, in those cases, pretty good densities from the simulation. I mean, you can say they're not as sharp as a real crystal that diffracts out to 1 angstrom would be, but I think the differences are not all that great.
And I have to say, we're all very much looking forward to seeing what you find out about the diffuse scattering with Nozomi and Steve. Thank
Sure.
you.
Thanks. Who has, go ahead, Gail, you can pass the microphone around to whoever should be next.
I have a question about the dynamic and the static disorder that you mentioned early on.
Mm-hmm.
Is the static disorder similar to local strain? And the question is, can you distinguish between the two in X-ray?
Yes, okay, good question. Yes, some aspects of local strain would be in my static model. Of course, this is kind of an idealization to call it static versus dynamic. Yes, time averaged crystallography at a synchrotron, in principle, can't tell the difference between those two. And now, free electron laser experiments, which you have femtosecond pulses and so on, potentially could help you distinguish between thermal motion and static disorder. But for the sorts of things that we have, you can't. As I said, it turns out that in the kind of handful of simulations we've done so far, because not only there are only a handful of measurements, there's only a handful of simulations, the two things look like they're kind of about the same magnitude. And I don't know if that's even a generalizable statement or not. And, of course, our measures, we might hope that our measure for dynamic disorder is about right, because we're doing molecular dynamics at the right temperature. But surely our model for static disorder, which only has a few unit cells and so on, is probably missing real features of real crystals that are important. So I would have much less confidence in what we're seeing for what I'm calling static disorder as actually being realistic of what's really going on.
Do you think that, I mean, with this diffuse scattering and really sensitive detection and molecular modeling, do you think that there's the possibility of determining structures of, let's say, intrinsically disordered regions in proteins? Or is that still too far?
Well, we're going to try things. I don't know if it completely intrinsically disordered is going to come up.
Well, it's certainly more flexible.
Yeah, I mean, other methods, NMR and other things give you lots of information about disordered proteins. The problem is that there are really lots of different ensembles, if you want to say, that could give you probably the same electron density. And so then that's a much harder problem, saying, if you have disordered regions or even loops or something, there's lots of ways that could be modeled. And do we have enough ability to choose the right models from the wrong models is probably not there yet. But we're going to try to do refinements against both diffuse and Bragg data simultaneously. Probably not initially, certainly not initially on an intrinsically disordered protein, but that's a long-term goal.
So experimentally, it's really hard to measure water and their dynamics in the interiors of protein. But I think diffuse scattering might give you a very good way of looking at them. So I was wondering, are there any relations between, the maybe like 4 hydrogen bonded water versus hydrogen bonded, like water hydrogen bonded with protein side chains, and how they kind of manifest themselves as diffuse scattering?
Yeah, I don't know the real answer to your question. I just point out the difficulty of X-ray scattering is that any particular angle, any particular pixel that you're measuring, or any particular spot in reciprocal space that you're measuring, of course, is getting scattered photons from every place in the unit cell. So you're doing a big averaging over the solvent to see that, and that might not be the best type of spectroscopy to get at individual waters, or you might need to do different things. I mean, the averaging problem is a severe one. That any electron, any place in the unit cell, or any water molecule, any place in the unit cell, can scatter photons into the same pixel, and so it's hard to pick out then let's say a small number of funny waters or surface bound waters or something from the bigger background of other waters, but we'll see.
Okay, last question.
Really great talk. I was wondering if you could comment more on the dielectric screening, because if you have, let's just assume that you have the right number of water molecules in there in the unit cell and they're moving with the appropriate thermal energy, wouldn't that be the extent of the dielectric screening that's experienced?
Yes, so if we're doing the simulations, we think we have a good model of dielectric screening. We know that the dielectric constants of water are about right, and we're doing that right. My comment about that was, suppose you were doing a refinement and you only have a small number of waters in the refinement. So your model, if you look at any PDB file, the number of waters in the PDB file is much smaller than the real number of waters. And so if we're refining against that model, which is what we're doing right now, then we're missing some aspect of that. And so that, you can think of various reasons. I had some slides that I had to skip over that kind of, we're thinking about that, and we have ideas about how we might be able to handle that problem. So, but initially, if you just say do it today, and what Phoenix does right now, that's a current problem that is one of the issues that we have to work on, right? It's not, we have ideas, but it's not by no means a solved problem right now.
So like this would be a representative of one of the things that might deviate from the crystal data, yet also in other metrics result in better accuracy.
Yeah,
the absence of waters in the crystal structure, for instance.
Yeah. Something has to be done about that, and I don't know what the best approach is. Okay, thanks very much, everybody.